Hello, you are going to learn slightly, according to me, a slightly difficult topic, which is called singularity solutions of Stokes flows. Okay. So, we have considered Stokes flow past a sphere and then Stokes flow past a cylinder by using a stream function, and we have gone for a separation of variable solution, and then we could solve the Stokes flow past a sphere problem and then get the corresponding force acting on the sphere. Okay. So, in order to discuss little more advanced problems, in particular flow past microparticles. When I say microparticles, these are like bacteria or motility of sperm, etc. So, these are having very irregular aspect ratios. So, as a result, solving using usual numerical methods, etc., analytical anyway ruled out, but even solving using regular numerical methods will be very challenging. So, in order to handle such situations, something called singularity solutions of Stokes flows. So, that is very much handy. Okay. But I am giving a caution. So, this is slightly difficult topic. So, please pay attention, and since the scope is limited, so we will try to cover some relevant topics. Okay. So, what do you mean by singularity? So, like something blows up at a particular location, we say that is a singularity. Okay. So, to understand singular solution of Stokes flow, so let us review just quickly Laplace equation and the corresponding singularities, because it is relevant. So, that once we understand that, we can go for Stokes flow. Okay. So, the first function which comes to our mind is a step function, that is the Heaviside function. Okay. So, the definition is as follows. So, this is a Heaviside step function. Since we are referring origin, so this is a h of x only. So, the definition is h of x is 0 when x is less than 0 and 1 x is greater than 0. Okay. So, that is the definition, okay, greater than or equal to 0. So, it is a step function. So, this is more relevant, and then the next function that comes to our mind is Dirac delta function. So, that it is defined as follows. It is 0 at x not equal to 0 and it is unbounded at x equals to 0. Okay. And with the corresponding property that the total integral is 1. So, now you might be wondering what is this function, this Dirac delta function. So, it is a point source. So, it is like, so you apply infinite stress, okay, force at a particular point. So, the stress generated at a point source. Okay. So, that will, when the point is shrinking to 0, whatever the stress generated, that is supposed to be infinite. So, that is the Dirac delta function. So, this can be defined in various ways using various limiting functions. Okay. So, it is hard to realize how this integral is becoming 1 etc. So, let us have a quick look at one of such definitions, but there are many like that. So, if you consider a function f and t which is defined as n when mod t is less than 1 over 2 n and 0 otherwise. So, here if you see, if you consider f 1, so let us say these points are minus half and half. So, then f 1 is defined as 1 when mod t is less than half, 0 otherwise. So, that is this box. Okay. So, then f 2 is 2 when mod t is less than 1 by 4. So, it is okay. So, this box. So, like this, if you keep on increasing n, the total area remain the same, but the strip becomes thinner and thinner, and as n goes to infinity, f and t approaches the delta function. Okay. You can see a thin line shoots up to infinity. Okay. So, this is a standard way of defining Dirac delta function, but there are several such examples. For defining Dirac delta function, one can consider several functions which will give in the limiting case Dirac delta function. Okay. Okay. So, it carries several properties in 2D that can be extended, the definition of 1D that we have given. So, this is at a point in R2, it is 0 at this, if it is non-zero, and then if it is 0 here, then it blows up, and again the total area remains unit. Okay. Now, it shares an interesting property that is called a shift property. If f of x is taken convolution with the delta function, then the total value is the function taken at a. Okay. So, you can see the Dirac delta function definition can be extended to any x naught. Okay. So, this is unbounded x equals to x naught 0. So, this can be need not be origin. So, we have shifted. So, now correspondingly the definition satisfied is f of x delta of x minus a, this is the shift property. Okay. So, we have a Heaviside function. So, that also can be extended. Suppose this is x equals to 1. So, then one can define. So, this is 0 and then 1. So, this is h of x minus 1. So, this will be 0 when x is less than 1 and 1 x greater than or equal to 1. Okay. So, that is one can define like this. Okay. So, now these two share a relation. So, I just give a remark, the proof will be maybe we supply as an appendix. So, this share interesting relation h dash of x is delta of x. That means, the derivative of the Heaviside function is Dirac delta function. So, this requires some concept. So, this is called weak derivative. So, my apologies to use this term, but you understand as a notation the derivative of Heaviside function is a Dirac delta function. Why I said because this is, as you see, it is a step function. So, there is a discontinuity, right. So, now when you talk about the derivative, so it is not in usual sense, that is not in classical sense, it is a weak sense. So, what is the weak derivative, etcetera. So, the concept is involved. So, for the time being, maybe a simplified version we will put it in the notes, so that you can understand little bit more. Okay. So, apart from this, there are several properties. This can be done at 0. Okay. We can show it the same shift. If it is delta function, this is obviously f of 0. So, this can be done very quickly. So, you can see, consider this convolution, then if you integrate by parts, this is f of x into h of x at these limits, then this. So, this is going to 0, okay, because of the definition of the Heaviside function. Then you are left with this. We apply definition of Heaviside function, then you get this. So, the proof for this is exactly similar lines. So, only thing it is shifted by a. Okay. So, this is one property. Similarly, there is a scaling property that Dirac delta function satisfies. A x is 1 over mod a delta x if a is non-zero. Okay. So, these are standard definitions. Yeah, this is a shift that already we have indicated. Okay. So, now once we discussed Dirac delta function, so we are going to define the singular solutions, okay, of Laplacian. So, before we do that, we discuss something called fundamental solution. So, what is a fundamental solution? Solution of a differential equation defined over an unbounded region for a point source of unit strength. that is also called free space Green's function. So, what do you mean by this? If you take some differential equation, some operator L u equals to 0. So, where L is a differential operator, then the fundamental solution we are saying you consider L u equals to delta of x. If we solve the corresponding equation, whatever we get, suppose if we take L u is point source, then whatever the solution you get, that depends on these two. So, and if you do not use any boundaries, then whatever the solution of this particular equation, so that is called the fundamental solution or free space Green's function. Okay. So, that is what I indicated for Laplacian. If you consider Laplacian, if you take del square v equal to delta of x in a domain D in the absence of any boundaries, whatever solution we obtain, that is called Green's function, free space Green's function. Okay. So, now the question is how do we get this? Okay. So, when we say a point force at a particular point x naught, so singularity, so we expect it is a source or a sink. So, what do you mean by this? If it is a source, we expect flow is radially symmetric and something is coming out of a dot, and if it is a sink, then we expect something is going in. Okay. And of course, one can define if you source of large intensity, so the more flow comes out. If it is a sink, more flow from the environment will be sucked inside. So, this is a general sense. Okay. This is a point source, point sink. So, we have to consider the corresponding solution. So, we consider this, and as I indicated, point source has a radial symmetry, that means only the impact is along the radial direction. So, therefore, it ensures that V is function of V of r. Okay. Then we expand the Laplacian considering only radial symmetry, so that there is no theta dependency, and we are in 2D. So, the Laplacian reduces to this, and the right hand side is delta function, which means this satisfies homogeneous equation for r greater than 0. That means, if you puncture, if you remove r equal to 0, it satisfies homogeneous equation, right, and one can write quickly the solution. So, what we are considering is you have a point source. So, this is x equals to 0, and if we consider the solution V of r, it behaves like okay. So, typically in R3, if you consider some flow at a particular point, as you go r goes to infinity, naturally its impact goes to 0. Okay. That is typically in 3 dimensions. But in R2, if you consider similar condition, so this is the source we are talking about. Okay. In R2, if you consider similar condition, so it admits a logarithmic singularity as r goes to infinity. So, therefore, how one determines B is we normalize the intensity of this on a unit circle. So, simply we consider r equals to 1, and then we say that V goes to 0 on r equals to 1. So, this will give B equals to 0. Okay. So, that will indicate that V r is behaving like ln r. And what is this A? A is called strength of the singularity. A is called strength of the singularity. Okay. So, how one can determine A? So, we can have a, so this I have already indicated, we go for r equals to 1 and then we normalize. So, how to determine the strength? So, you consider a disk of radius epsilon centered at this point. Okay. Then if you consider this, by virtue of the delta property, that is 1, and by virtue of the corresponding fundamental solution, that is a Laplacian. Okay. Now, we use Gauss divergence theorem. So, if C epsilon denotes the boundary of the disk d epsilon, then by Gauss divergence theorem we get this, and since it is a circle of circumference 2 pi epsilon, we get simply this is the flux dV dr, and the corresponding element is a corresponding line element r d theta, that is considered. So, that will be epsilon d theta, and the dV dr is a by epsilon. So, what we get is 2 pi a. So, this implies a is 2 pi. So, that means we have determined the strength of free space Green's function in 2 dimensions. Okay. So, now without mentioning the proof, we also indicate that if we take any point x bar, where x bar is in R 3, then we get the corresponding solution in 3D behaves like B by R, and the strength can be calculated using similar arguments. Okay. So, this is the corresponding Green's free space Green's function in R 3. Okay. So, these are little since this course requires some knowledge about PDE. So, I assume once with these explanations you will be able to get the corresponding derivations. Okay. So, this is the 2 dimensional free space Green's function, and 3D as I indicated. So, this is the corresponding free space Green's function. Okay. So, now we got the corresponding singular solutions of Laplace equation. Okay. So, we can use these singularities to represent a particular solution about Stokes equation. Okay. So, before we do this, let us consider point source. So, that is nothing but, now instead of considering delta function, we are considering of some strength m. Okay. So, then the solution of this will be given by, so this plus or minus. So, it depends, sometimes we take plus for source, sometimes minus for source. So, that is not an issue, we can absorb in this and call it some m prime. Okay. So, it indicates only the direction, source or sink indicates the direction. So, in 3D this is the point source, that is nothing but the velocity potential corresponding to a point source at x equal to x naught, which means we are talking about x equals to x naught. So, in that sense r will be okay. So, when we say this, r is this. Okay. So, that is the point source. Now, one can represent phi is harmonic because it is a velocity potential everywhere except the point x naught, because it is a singularity. So, it determines an irrotational flow, hence a Stokes flow. So, let me explain this statement. So, any vector field can be decomposed poloidal, toroidal. So, that means this is the rotational and this is irrotational. Okay. Now, if you ignore rotational and consider only irrotational, we have V is grad phi. So, this if we go for usual conservation of mass, that is divergence free, combining these two, we get del square phi is 0. Okay. So, which means we have phi is harmonic. Okay. That means, when we consider Stokes flow, and restrict to rotational flow, what we get is, so they commute and this is 0, this implies we get 0, this implies P is constant. So, therefore, the conclusion is V P given by constant is a solution of Stokes equations. And what kind of solution? This is a irrotational solution. Okay. So, this is a particular. So, therefore, what we now think is, you have potential flow and you have a singularity corresponding to the potential. Now, just now we have shown that any potential also solution of Stokes equation with constant pressure. Therefore, once you have a singularity corresponding to potential flow, maybe we can get the corresponding singularities of Stokes flow as well, right. So, this is what we are anticipating. So, let us see how the corresponding singularity solution we can get from Stokes flow. Okay. So, we have the potential source we are calling. So, that is due to the Laplacian, which is given by gradient of scalar. Now, if you have potential, we know what is phi in 3 dimensions. Therefore, the velocity is given by the gradient of phi, which is this. So, then we can get the corresponding velocity potential. So, I am calling m here as mu. Okay. So, that is maybe I should have used a unified notation. Okay. So, how we are getting? We have phi equals to say m by 4 pi and 1 over r. So, this is by virtue of, this is nothing but point source solution due to potential flow. Okay. Now, we have shown that V bar equal to grad phi, P equal to constant is a solution of Stokes flow. Therefore, what will be singular solution of Stokes flow? So, that is nothing but, so this is nothing but in index notation. So, this is nothing but okay. So, this is we get and derivative of r with respect to x I, that will be okay. So, the corresponding velocity due to the potential is given by r cube. So, this I have written it as opening the completing the summation. X I means if it is about if the singularity is about origin, then R is nothing but, if it is about, then R is nothing but. Okay. So, therefore, this is nothing but generalizing. Okay. So, this is the corresponding singular solution. Okay. So, once we have the singular solution, P is constant. So, these two together will be solution of Stokes law. Okay. Then the question comes, can we compute the corresponding stresses? Yes, we can compute the corresponding stresses. Okay. So, consider the expression for the stresses. T I j is mu Okay. So, now we have u I is mu by 4 pi x I by r cube. So, we can compute the corresponding stresses. T I j is, this mu is viscosity. So, let me call this is some strength, otherwise it will be misleading, some mu tilde. So, mu, then this is common. Okay. So, I am leaving this part. Okay. So, we can normalize. So, now dou u I by dou x j, right. So, that will be u I is, so we have to dou by dou x j x I operating on x I by r cube. So, this is mu, first one if you operate. So, this we have to use u v formula, right. So, if we do this on x I, what we get, when x I equal to x j, we get 1. So, therefore, delta I j by r cube, then on this if we do minus 3 x I by r 4, then x j by r. Okay. So, the first one we have to operate on this plus dou by dou x I on u j. So, that will be x j by r cube. Okay. So, this if we do again the same way, we get again so this time R 4 here. So, what we get, the corresponding stress is 2 delta I j by r cube minus 6. Okay. So, it is very easy to calculate the corresponding stress. Okay. So, what we have done just now is we have considered the potential singularity. Okay. So, then using the potential singularity, we have computed the corresponding singular solution of Stokes law. Okay. So, now once you have a singularity, if you differentiate the singular solution, what happens? That is the next question. So, if you differentiate, we get higher order singular solutions. So, let us see that. Suppose we consider a potential derivative with respect to source point is a higher order singularity, that is called a potential dipole. Okay. So, if d denotes the strength of a potential dipole, G d located at a point x naught. So, then the derivative with respect to point source is a higher order singularity, it is called a potential dipole. Okay. So, which means we have the corresponding V s. So, this if you generalize, what is our V potential source? So, this is some strength. So, that we can ignore. Then we have x bar minus, this is the general sense. In summation notation, we are writing it as x I by r cube. So, here x I strictly speaking, where x naught I where x I is x I minus x naught I, that is these are the coordinates with respect to the singularity. Okay. So, now we are talking about derivative of this with respect to the coordinates. So, then this is called potential dipole. This is called potential dipole. So, you can see the singularities of order r cube here. So, if you differentiate, it will be much more singular. Okay. So, this can be obtained very much. Okay. So, remember we are differentiating with respect to the coordinate. Okay. So, in summation notation, okay. So, j let us say, then v in summation notation. So, this if you execute here x 0 is sitting in this, right. So, there will be a negative sign when you differentiate this with respect to x 0 j. So, that you have to. So, therefore, by virtue of this will produce, okay, then minus will give first minus, then next time when we get another minus. So, therefore, here we get. So, this is the corresponding solution for the derivative singularity, which means this also represents a potential solution, but also represents solution of the Stokes flow, and the corresponding pressure. Please think it is very easy. That means, we are asking potential dipole P given by what is a solution of Stokes equation. Okay. So, I have shown you for the point singularity. So, now for potential dipole you can very easily get what is P. Okay. So, these are very elementary singular solutions of Stokes equations, but one can derive an arbitrary solution of Stokes equation. So, that is definitely much more involved. Once we get any, so when I say potential, that is only we are considering irrotational, but if you consider arbitrary flow and then get the corresponding singular solution, that will represent the complete flow structure, and that can be used for solving any arbitrary flow. So, that is much more involved, but with this I am sure you get some idea about singular solutions of Stokes equations. Thank you.